Alrighty, happy Easter, everyone. Today's lesson is actually going to be delivered by a former student of ours, Alan Wu. I had the pleasure of teaching Alan in my first year at Mount Albert back in 2014 in my 12 stats class, and he would always go beyond kind of what we were learning at the time. He would design simulations on Microsoft Excel. He loved the computer programming aspect. And then when it came to calculus, we always had good discussions around the not just the problems themselves, but how you go about solving them. And so that kind of flows in this lesson. You're going to see that a lot of what Alan goes through is explaining how to think about the problem, because he is covering a strange problem. I gave him two questions to do. He chose. We did both, but he chose to deliver the more challenging of the two. He's always liked inequalities and the maths behind them. He went on to achieve outstanding scholarship in 2016, and now is at the University of Auckland doing really well. So today's problem, like I said, it's an interesting one, something that we probably don't normally see in the scholarship course/exam, but really good for the mathematical thinking involved. Prove that among any four distinct numbers from the interval 0 to pi over 2, so you have an open interval for a start. Those round brackets mean not inclusive. You can't pick 0 or pi over 2 as two of your numbers. If you choose any four distinct different numbers from that interval, there are two such that this inequality here holds. So without further ado, I'll let Alan take over the lesson, and we'll catch you tomorrow.
Hi everyone, it's Alan here. Today we're going to do a problem from Mr. Roland. So here's the problem. Prove that among any four distinct numbers from this interval, 0 to pi over 2, there are always two numbers, say x and y, such that this messy inequality is here. So the first steps to do it is to simplify this messy inequalities, because I don't know what you think, but to me that looks quite bad, and we definitely want to do some work. So we're just gonna use your normal trigonometry identities, and you do that for left hand side and right hand side respectively. So when you face this kind of problem, I think which identities to use is actually quite important, because that can be the difference between solving it in two lines, or well, maybe even take much longer, like 10 minutes to do it. So choose wisely. So it's your turn now. You have some formulas here, and you want to think which one you want to pick. So we're just gonna focus on the left hand side here. Think about which formulas you want to use to simplify it. So when you do this, you predict what happens when you substitute that formulas in. And I'm going to give you 30 seconds to think about it. Okay, did you get that? Which one did you pick? So if you pick this one here, this one right here, I think that is a bad choice. If you pick that one, good luck. It's probably going to take you a while. The reason for that is that you have all those cosine x, cosine y, and sine x, sine y all over the places, and you don't even have sine on the right hand side, so that is a bad choice. I think the good choice is this one, this product here, because you have cosine x, cosine y, and if you predict what happens when you sub that in, you get cosine x plus y, cosine x minus y, and then you can apply that formula again to the cosine x minus y. It's going to simplify quite nicely because you have plus and minus. So let's just do it. Purely mathematical work. So the first step, just write down the formulas, and that is the right hand side for reference. That's your left hand side. So first, to sub in that formulas into it, the product formulas, and we can see is, yeah, that's the result. The next step, you apply that formulas again. So you get x plus y plus x minus y, so you get 2x, and x plus y minus x plus y, you get 2y. Then that one, the square here, that is just multiplying that twice, because you get cosine x minus y, and multiply the cosine x minus y outside the bracket. So we have this form here. Looks, well, simpler. And you see the 2x here. We can use the double angle formulas to get that closer to the right hand side, because if you apply that, you're going to get a square. So it's going to cancel out quite nicely if you do that. So nice and easy so far because we picked the right formula. Okay, now we sub back our Trig's identities into the inequalities, and then we just rearrange it a little bit. We get cosine square x minus y is greater than 3 over 4. So now the next step is to solve this. So we need to use the fact that cosine is an even function. Well, you don't have to, but that's one way to do it. So if you write it like that, you can rewrite that as the absolute value of x minus y. And now you have two numbers, x and y, within this interval 0 and pi over 2. You know that the distance between any numbers within this interval must be between 0 to pi over 2. So you know that cosine of that number is between 0 and 1. So because you know cosine is positive, you can just square root both sides, and you get that. The next step is to notice that number on the right, root 3 over 2. That is just cosine pi over 6, right? So we can use that to solve this inequalities. We need to remember that cosine is decreasing on this interval. 0 pi over 2 is decreasing because you can look at the unit circle on the right. So therefore we can solve this to this nice simple absolute values inequalities. Wait a second, what just happened? We went from this, well, to this. Not bad, huh? Not bad. In fact, if you set that interval limitation there, then you can go in the reverse direction. You can go from this simple thing to this complicated looking things. Back to the question here. We can so we're going to use our simplified version of inequalities to replace that messy one up there. And because absolute values have meaning in terms of distance, right? So we can rephrase our question into perhaps an easier version of the question which we were trying to solve initially. So you can see there's no more tricks here, but still a rather strange problem to prove, I suppose. So, okay, this is our new statement. Prove that among any four distinct numbers in this interval, there are always two numbers. We can always find two numbers that are less than pi over 6 distance apart. So is this even true? Does it sound like it's true to you? We can play with some examples here. So I've prepared little animations. I'm just gonna play it. So you can see that we can move around this red point and the blue point, the blue bar. So the blue bar is a line, is a segment that is pi over 6 length. And if the blue bars crosses 2 points at once, that means the distance between the 2 points are less than pi over 6, otherwise is more than pi over 6. So our goal is we want to move those 4 points in a configuration that we can never cross 2 points at once with the blue bars. So let's do it. Just gonna put little animations here. So as you can see from the animations, as you make up space for 2 points, you're kind of losing space for the rest of the points, and at the end you just can't do it. The blue bar can always cross 2 points at once. This should give us some very useful insight in terms of proving it. So the first insight is to note that no matter how the 4 points were distributed at the beginning, we will always end up spreading 2 points at a time and eventually spreading all points out. So we should expect 2 of the points sitting at the end point that is just slightly above 0 and slightly less than pi over 2. So now we have 2 points fixed, just 2 points left to be moving. If you think about it, it's kind of like breaking a stick into 3 segments. So you break it twice, you get 3 parts. So the key thing here is to notice if you set one segment greater than pi over 6, then you only have less than pi over 3 left for the other 2 segments. And this breaks the problem into a simpler problem. So we are breaking a stick into 2 parts, which the length of the stick is less than pi over 3. And this is actually very intuitive, I think, and very straightforward. So you have 2 parts, either one part is greater than the other part, or the 2 parts are equals. So you can see that if they're equals, then they are still less than pi over 6 because the total length is less than pi over 3. But if you have one part greater than the other, that means one part is going to be greater than pi over 6. Well, maybe greater or equal to pi over 6. The other part is less than pi over 6. So yeah. So if you don't like that way full of text, you can do something more symbolic, like you usually do. So we can let the 3 segments that we broke into be x, y, and z. So we have x plus y and z sums to be less than pi over 2. And then we can set x as less than or equal to y, and then y is less than or equal to z. That doesn't matter, it's just whatever you name it, because yeah, you always have some order between the 3 numbers. And now we want to maximize x. So x is the smallest number. We want to maximize that smallest number. If we can prove that number is smaller than pi over 6, then we are done. So this is an optimization problem, right? So how do we solve it? Often when we think of optimization problem, we might think of using calculus, right? But unfortunately, this optimization problems have 3 variables to optimize. It has at least two variables to optimize. So the calculus we learned, the single variables calculus, we can't do it. You have to use multi-variable calculus, stuff like this. So no calculus. So what does that mean? Can we find another way to do it? Well, actually, calculus is quite often not the answers to a problem. Calculus provides a very systematic ways to solving things, but quite often we can find more elegant solutions without the use of calculus. Well, not always. Calculus definitely helps in a lot of scenarios. But for a lot of problems, calculus actually makes things more complicated. In fact, before calculus was even invented, in the 17th centuries, many optimizations problems were already solved without the use of calculus. So this guy here, Euclid, so that was 2000 years before calculus was born. He solved a lot of geometric optimizations problems without calculus, of course. So in our case, we have to look for another method. And we can actually use linear optimizations, so-called linear programming. So because all the inequalities here, all the conditions here, they're linear. So they're just linear stuff. We can use linear programming. This linear programming problem has three variables, which is kind of unusual. So we have to use a little tricks to make it into a two variables problem. Actually, my bad. I said that having three variables in linear optimization was unusual. It was actually very usual. What I was trying to say is that it's a bit tricky at level 3, or scholarship, a little bit. It's actually quite usual for linear optimizations problems to have multiple variables. They can have like 10 variables or whatever, a lot of variables. So we're gonna change that inequality there, x plus y plus z less than pi over 2. We're gonna make it equal to pi over 2 minus k, where k is a very small positive constant. And then this becomes our standard scholarship level linear programming problems. So we have our constraint here, and we have our profit functions here, just simple x. We want to maximize x, and then we substitute that from that equation, substitute that z into this inequality here, and we get this. And we rearrange this, we get this. Note, bear in mind that we also have this restriction set for our variables. So now we can do it. So just plotting the first two constraints, we can already see that x is maximize happens that when they intersect, because I think you can see from that graph there. So that is x equal to y equal to pi over 6 minus some very small constant, and substitute that back, we get c is also equal to x equals to y. And then we need to check if it satisfies all the conditions we set from the beginning. So this condition, yes. Next, yes. So yes, we have x. That is indeed the most optimal solutions. That is pi over 6 minus k over 3. So we have x smaller than pi over 6. So you don't like linear optimizations? So if you're lazy like me, you don't want to do linear programming, I can show you the ultimate method for solving this problem. So both linear programming and calculus were somewhat kind of recent methods. But a lot of optimizations problems were solved without any of these methods, but they were with inequalities. In our case, we don't actually need to use any fancy inequalities to solve it. We can just make use of very simple properties of inequalities to solve it. So this method is kind of like the symbolic method of the first method I show you that is full of text. So if you convert that into symbolic, it will look like this. So first we suppose x is greater or equal to pi over 6, which we know is not true, but we're still going to suppose it anyways. And because x is smaller than y or equal to y, we must have y also greater than pi over 6 because x is greater than pi over 6, right? And because y is smaller than z is greater than y, so we also have z is greater than pi over 6, greater or equal to pi over 6. And so we have x, y, z all greater or equal to pi over 6. Now we add them together. And we get x plus y plus z greater or equal to 3 pi over 6, which is pi over 2. So, well, if you look at this contradicts with the conditions that says the sum of the three numbers together is less than pi over 2, because we now say it's equal to or greater than pi over 2. So that means our assumption x greater or equal to pi over 6 is not true. Therefore, x is less than pi over 6. Cool, isn't it? That's my favorite method. I think that's quite cool, simple and nice. Thank you for watching. I hope you enjoy these problems. Enjoy your weekend. See ya.